The next question is it an abelian group? Now, what was that again? Well, the point was that in these prerequisites for being a group, what is missing in these axiomas, is maybe a better word, is the thing of the commutativity. And is this law applying here? Yes or no? Well, let's have a look at that. So it needs to be true that if I have A multiplied modulo 5 times B must give me the same result if I reverse the order, and obviously from the symmetry of the Cayley table I know that it is true. So this group is indeed an abelian group. And the last point is the question of isomorphism. So I have this group Z5 without the 0 with the operation multiplying modulo 5, and I take another group which is Z4, the first 4 elements of Z, combined with the addition modulo 4. And the question is now, are these isomorphic or not? Now, in order to answer this question, I go back to the definition. I'll take my example. I mentioned I had the positive real numbers, and the other set was the set of real numbers. Here the operation was multiplication, here the operation was addition, and I saw that there was this bijective relation, the relation being the logarithm, and secondly, that was true that if I had two elements A and B, that the log of A times B equaled the log of A plus the logarithm of B. Now there's another way to show this. If I do this with Cayley tables, then it should look like this. I have two Cayley tables. Here I have for instance, my operation star, and I have an element like A, and this A has an image A with this little accent there. For instance, in this case it would be A and the logarithm of A, and here I have another element B which has an image B with an accent. For instance, in this image it would be B and the logarithm of B, and here I have the operation circle. Now first of all, every element needs to have an image, so every element B needs to have an image B accent, and A needs to have A accent, and it has to be true for every element of the set I am working with here and the set I'm working with there. And that was the first requirement. The second requirement is that the operation A star B needed to be the same as the image of A operation circle image of B. For instance, here the logarithm of A times B, it needs to be a star operation, gives me the same result as the log of A being the image of A plus the log of B being the image of B. Okay, so these two needs to be the same. Now, how does this work out in our situation? Again, I have the Cayley table. We already looked at this. The multiplication modulo 5. Here I have the numbers 1, 2, 3, 4 and 1, 2, 3, 4. And I had my table which I already mentioned very briefly. It was 1, 2, 2. Then it was 3, 4, 3. Then I had 4, 1, 1, 4. I had 3, 4, 3, and 2, 2, and finally 1. Now, if I compare this with the Cayley table of the other group, the operation is addition modulo 4, and the elements I have are the first 4 elements of Z being 0, 1, 2, and 3. And if I fill out this, 0 plus modulo 4, 0 gives me a remainder of 0. 1 plus modulo 4, 0 gives me a remainder 1, and so on. And if I continue, the other results are 1 plus 1 gives me a remainder of 2. Then here I have a remainder 3. Here I have a remainder 0. And here again I have the remainder of 1 and remainder of 2. Now if I look at the structure of this table, I see that it is beautifully, all these 2's on a row and all these 3 and so on. And can I find this structure here as well? Well, indeed I can, by switching the 3 and the 4. Now I can't imagine this is a bit of a surprise, but if you would do this, if I would switch these 2 columns and again also here these 2 rows, what would happen then? This 4 goes there, the 3 goes there, and so on, which gives me in the end the result. Okay, so I swapped these rows and I swapped here the columns and here the rows, and now you see that these 2 Cayley tables have the same structure, because I have also here a number of 3's on a row, a number of 1's, and so on. And now I can say, look, the function I'm defining is that the original 1 is mapped on the image 0, 2 is mapped on 1, 4 is mapped on 2, and 3 on 3. And then, for instance, I see that what I had here is, for instance, now this 4, which is then mapped upon the 2. put this in other words, if I have 2 multiplied 5, 2, obviously this gives the result 4, and I apply the function, then this should be the same as the image of 2 plus modulo 4 the image of 2, which is then, of course, obviously 2. Now, is this correct? Let's have a look. I have the image of 4 being the result of 2 times modulo 5, 2. Is that now the image of 4, is that now 2 being the result of this operation? Well, let's have a look. I had here the original 2, which was mapped to the image 2. I had the original 4 mapped on the image 2. And indeed it is true, and you can prove that it is true for every element. And therefore this is isomorphic.